When space debris enters Earth's atmosphere at 15 kilometers per second, its destructive potential is kinetic energy rather than chemical explosives. This geological scar is the Barringer crater in the Arizona desert. 50,000 years ago, a 50-meter-wide asteroid punched straight into the crust. The impact instantly excavated millions of tons of bedrock. It transferred 10 megatons of kinetic energy directly into the ground, leaving a bowl deep enough to hold the Burj Khalifa. Our simulation considers a second rock, YR4. At 60 meters across, it is comparable in size to the Barringer asteroid. However, its trajectory directly targets the dense urban population of Bogotá, Colombia. Despite YR4 being larger and releasing 15 megatons of energy, it generates no cratering. It never touches the ground. Size and speed alone do not dictate the type of devastation. The altitude at which the kinetic energy is released changes the mechanism of destruction. The 1908 Tunguska event in Siberia serves as historical precedent for these mid-air detonations, flattening an estimated 80 million trees in parallel lines. Researchers investigating the site found radial destruction across hundreds of square miles, yet they discovered zero evidence of an impact crater. The Tunguska object detonated high in the atmosphere, creating a downward shockwave rather than an outward seismic wave. To understand how an object can level a city without striking it, we must reverse engineer the fluid dynamics of hypersonic atmospheric entry. An asteroid transitions from the vacuum of space into the upper layers of Earth's atmosphere at 15 kilometers per second. At hypersonic velocities, atmospheric gas molecules cannot move out of the way fast enough, causing the air to behave as a dense fluid barrier. This creates ram pressure, the intense physical compression of gas directly in front of the falling object. This pressure generates extremes of heat and mechanical stress across the leading face of the asteroid. In this fluid dynamics problem, the atmosphere acts as a solid wall, attempting to instantly halt the object's momentum. The survival of the asteroid depends on the battle between the atmosphere's compressive force and the rock's internal strength. The Barringer asteroid was a solid, dense chunk of iron and nickel. Its internal structural yield strength was greater than the atmospheric ram pressure, allowing it to punch through the air like a bullet to strike the bedrock. In contrast, the YR4 object is a porous, structurally weaker rocky chondrite. At 10 kilometers of altitude, the compounding ram pressure exceeds the tensile yield strength of the rock, causing it to shatter. Material composition is the ultimate deciding factor. Structural failure in the upper atmosphere prevents the kinetic energy from reaching the Earth's crust. Following structural failure, high-pressure atmospheric gas violently forces its way into the newly formed microscopic cracks. This begins a fragmentation cascade, where breaking apart exponentially increases the total surface area encountering air resistance. The massive increase in drag acts as an instantaneous break, stopping thousands of tons of mass in a fraction of a second. Because kinetic energy cannot simply disappear, it must instantly convert into thermal radiation and a massive acoustic shockwave. This results in a 15 megaton detonation occurring entirely within the atmospheric fluid. An asteroid airburst is the violent, instantaneous halting of cosmic momentum by the Earth's atmosphere. In our Bogotá simulation, the thermal flash precedes the physical shockwave, arriving at the speed of light to scorch the city. The atmospheric overpressure wave propagates as a massive dome downward from the 10-kilometer detonation point. When the downward wave hits the surface, it reflects and merges with itself, the Mach stem effect, amplifying the horizontal crushing force as it sweeps across the city. Because the Earth absorbs none of the energy, the overpressure is dedicated entirely to shearing off surface structures and snapping infrastructure over a wide radius. Altitude acts as an amplifier for atmospheric destruction, making an airburst potentially deadlier for a sprawling human population than a ground strike. We cannot alter the fluid dynamics of the atmosphere, leaving us unable to stop a fragmentation cascade once an asteroid crosses the altitude threshold. Viable defense strategies, such as NASA's DART mission, rely on altering the object's orbital mechanics years in advance. Preventing this energy transfer requires ensuring the mass never interacts with our atmospheric wall.